We begin this series of video lectures for the use in Math 121 by an introduction or a reintroduction to families of functions that we're going to be seeing during the course. Let's start with some examples. Below we have a graph or a set of axes with 4 different graphs shown. And these graphs are the graphs of y equals e to the x, ln of x squared, and x to the 1/2. And just as a quick refresher, you should ask yourself which one of these lines represents which one of these functions. Give you a second to think about that. And then we'll take a look. Okay. So hopefully you recognize that there's 2 functions that grow very quickly, x squared and e to the x. So that would seem to indicate one of these 2 functions here. And there's some easy landmarks that will help us distinguish those. Y equals e to the x squared at x equals 0, y is equal to 0 as well. So right away we can tell that the green line here is the graph of y equals x squared. That leaves the black line as y equals e to the x, and we can verify that by saying that at x equals 1, y equals e to the, at x equals 0, y equals e to the 0, which is 1 as well. So it goes to the point 1, 0. So that's not too bad. We also recognize that there's 2 leaned over functions like this, and logarithms and x squareds, or x to the 1/2 rather, which is better known as root x, have those shapes. And we can do the same kind of landmark idea, or we can recognize relationships like inverse relationships, which should be familiar to you. The inverse of e to the x is ln of x, and so if this is e to the x, remember that inverses are reflected across the xy line, y equals x line, and so this red line here must be the graph of y equals ln of x, and this blue line must be the graph of y equals x to the 1/2, or square root of x. We can also do landmarks there. What's the square root of 0? The square root of 0 is 0, so that would go through the origin. That graph would go through the origin. And ln of 1 gives a y value of 0, so the coordinate here at 1, 0 would be part of the y equals ln of x graph. So there's some of the families of functions we're going to be interested in: exponentials, logarithms, and powers of x. Some other things that we can talk about are just properties to look for. And as we just saw some examples, e to the x and ln of x, and x squared versus root x, x to the 1/2, those functions are inverses of one another, and those share some symmetries. So those are symmetric across the y equals x line. So some nice relationships graphically between functions that don't otherwise look like they're closely related in symbols. Exponential functions, a few features about them. So if we're talking about e to the x, or I won't go to a general base yet, but a base like 2 to the x or 10 to the x, the simple ones, these always have a positive y-intercept. Just going back to the previous page for a moment, that's the fact that an exponential graph, if we continued it on, would strike the y-axis at one particular point, and it'll always be positive. In fact, the graphs are always positive, always have positive y components. So that's a nice feature about exponentials. They start positive and they grow and grow and grow. Logarithms, being the inverses, some features of them is that they grow slowly as x increases. That's the flattened out shape that we see, the concave down shape. They go slower and slower and slower actually as x gets bigger and bigger. And an important feature of their domain, remember that term, is that they're undefined for x less than 0. And this is functions like ln of x, log base 2 of x, log base 10 of x. We'll talk more about those in later videos. Powers of x, of course, that would be like x squared and x to the 1/2. These don't necessarily have a lot in common, but they all do at least go through the point 0, 0 or the origin. Once we get into higher powers, you can talk about the S-shapes and things like that. There's rules for specific subfamilies, but very little is shared between all properties or all powers of x. All right. What other things are going to be in our catalog? I mean, we're going to be using these features as just points and facts that come in handy from time to time. What other family should we be worried about in this course? Well, I think some of you will immediately think of the trigonometric families, the sine, cosines, tangents, exponentials, and so on. Maybe a little less familiar would be the inverse trig functions. And here we're talking about arc sine, arc cos, etc. Sometimes it's written on your calculator, it's definitely written as sine to the -1. We'll talk about that more later. We try to avoid that in the class for issues of clarity. What other ones have we seen? Well, polynomials, of course. Huge family there. So taking the powers of x and adding them, subtracting them. And that often leads you to rational functions. And just remember that rational here, a good way to remember is that it comes to ratios. That's its root. And that's polynomials over polynomials in a ratio. So fractions of polynomials. Ratios of polynomials as a set of rational functions. So those are the biggest families of functions that we're going to deal with, but there's also some that maybe are a little less familiar to a lot of students. The absolute values. The absolute value function occasionally shows up in applications, and so we're going to use it throughout the course from time to time. And another set of functions that come in very handy, especially when we start looking at limit problems, are piecewise functions. I'll describe those more in detail in a second, but they're functions that are broken up somehow. They're made up of these canonical families, but using different functions on different intervals of input. So in particular, so the trig and the inverse trig, we'll talk about those later. What else did we have there? We had rational, of course. Well, we had polynomials. Polynomials are straightforward. I think we all recognize those. X cubed plus 3x plus 5. And of course, we talked about rational functions a second ago. That would be something like x cubed plus 3x plus 5 over x squared minus 7. That would be an example of a rational function. The other ones would be the absolute value. And we mark that as a graph like y equals absolute value, vertical bars, of x. What does that graph look like? Or what does the graph of that function look like? It is the V shape. On this side, it's essentially y equals x. But then, remembering that the y value is the always positive version of x, it gets reflected when we talk about the graph. This is absolute value of x. Let's actually slide this in here. On this side, it's like y equals x. When x is negative, though, we don't take the graph of y equals x. We take the graph of its flipped version vertically, which is the graph of y equals negative x. And in fact, we can write it that way if we like. The graph of y equals absolute value of x is the same as the graph of y equals x when x is larger than 0 or equal to 0, and when x, the input, is negative, we take that negative number and we make it positive by adding another negative out front. And this is the piecewise form of absolute value of x. So these two things, these two formulations here, are equivalent. Obviously, the absolute value bars is a lot shorter to write than this longer form here, but they mean exactly the same thing. Other ways we can do general piecewise functions, there's no reason why it has to be something as simple as absolute value of x. We could have something more exotic like, I don't know, let's do an x squared for x greater than 0 and an e to the x for x less than or equal to 0. What would that look like? Well, it would be some interesting combination of the two graphs. This is the range, or sorry, the domain over which we use the x squared function. So when x is x is positive, we would have the parabola y equals x squared, and when x is negative and up to 0, we would have the exponential growth curve up to 1 here. And reminder of standard notation, if a point is included in a graph, we use a fill dot, and when a point is excluded from a graph, we use a hollow dot or hollow circle. And so we can see on this graph here, we would continue on with e to the x if that was our function. We would continue back this way with x squared if that was our function all the time, but it's not. On one domain we use one function, on another domain we use another function. And we'll be seeing these piecewise functions again as an occasional highlight throughout the course.